Okay, so moving now from Unit B to Unit C. So now we've sort of motivated the theory of simulation, and now we're going to start moving into how do we use tools of simulation. And so it's going to start in sort of like what types of software tools might be available, and then how do we use probabilistic modeling to kind of come up with the programming we need to make those tools work for us. And so moving forward, so homework B1 was due on Canvas, and so you notice it's available like up to 5 days after the due date, and that's because homeworks have a late policy. And so what should happen automatically is so every day kind of deducts 20%, and then after the fifth day, the homework disappears or the availability goes away, and the solution set will automatically become available. And fortunately, we have finally been, the grader for this class has gotten through the HR process as of this week. And so we finally do have a grader just in time to start grading the homeworks. So they'll, currently getting up to speed, and we'll start grading those homeworks. And so that's good news. There is another one of these Canvas activities available coming up, prepping us for the next unit. So that's due before lecture D1. Again, those Canvas activities are going to be a lot of them because they're meant to help you sort of keep you, assessing your comprehension as you go on through, but there's a heavy drop policy. So if you don't want to do them all, that's fine, because I think there's like 15 or so and you get to drop like 7. So don't mean to overwhelm you with these Canvas activities, but they are there just to give that weekly practice. And then homework C2 will formally be assigned in lecture C2, but it is already out there. In fact, I think some people have already submitted it. So it's available. That is a homework that goes over some content from this unit on random number generation. And if you want to read ahead, it tells you where to look in the textbook for that. Again, just reminders, arena competition. If you're interested in doing this for your final project presentation, I think the registration closes at the end of this month. So gather up your teammates. There was a question asked to me on like, is there a benefit or what would be the differences being from doing this so we will make some slight, we might have to make some modifications on what's required for like the types of data that you will use for this in order to make it used for your final project. But otherwise, it's identical. If you were to enter this competition, what's required for you for this course would be identical. You just sort of be getting your data and your problem statement from Rockwell and IISE. And so, but otherwise, as far as the class is concerned, we'd run it just like your normal final project. So what are the benefits? That this project tends to be a little more complex than maybe some of the kind of ones that people pick on their own. It tends to be a little more real world. It's recognizable among people who do simulation in industry. And so maybe it looks good on a resume to say that you went through the competition. So those are the reasons why you might do it. Do you have to do it? No, absolutely not. You don't want to usually only get a couple of people who end up entering into the competition. And they're just looking for a little bit of an extra challenge. And if you're interested in that, that's great. But if not, that's fine too. So just putting it out there and just letting you know the registration closes here at the end of the month. And then if you are interested in starting to work with Arena, just to kind of get an idea of what that's like before the first couple labs on it, you do have access to Arena via either the computers in the Brickyard or remotely available. And you can also download Arena freely, the student version, if you have a way to run Windows programs on your machine. Okay. All right, there we go. So there's also additional competitions. As I mentioned before, IISE also sponsors a discrete event system simulation competition using FlexSim. FlexSim is a competitor to Arena. That competition is more based on healthcare. They expect up to 4-person teams instead of 3-person teams. So if you're more interested in that, that's fine, but you won't get direct instruction in FlexSim, although all the stuff you're learning about discrete event system simulation should apply to FlexSim as well. So it should be pretty easy to pick up. And if you're interested in doing one in Simio or another, as long as it's a discrete event system simulation, I'm willing to consider it. Just contact me ahead of time and say, can I use this for my final project? We'll talk about it, and then we can move forward with that. All right, so that's all the administrative stuff. Are there any questions? Okay. There was a question about ICA policy, explaining why no backtracking was allowed in the previous ICA. And, I make decisions when I build the ICAs based on pedagogy, and that's just for that ICA. That was the decision I made, so I think asking me why there's no backtracking allowed in ICA might be like asking me why I decided to use blue instead of red on a figure. So it's just, I think I reserve the right to make those decisions on assessments. So you just have to work within that. All right, so the stuff that we talked about last time is we introduced how you, in theory, can use spreadsheets to do discrete event system simulations. And so that was an extra credit part of the first homework. If you like to do that, you could say, well, do I get the same results that I got in my hand simulation by implementing these formulas in this spreadsheet? And so last time we used a very simple example of, well, if you just had a single channel queue, like this one, so this is, we'll learn, if you're not familiar with Kindle's notation, we'll talk about this again later on when we actually get to formally and stochastic modeling of these types of processes. But the basic idea is if you have a single server, a single resource, and you've got a single stream of entities coming into that, then we're trying to model how long that they wait. And so we can do this via the hand simulation, and I kind of went through the steps of it, and I'm not going to go through in great detail here because we'll revisit a more complicated example here in a second. But I basically walked through last time how instead of saying simulating what happens at every time step, instead, in a spreadsheet, if you want to do a discrete event system simulation, you come up with the relationships between customers from one customer to another across time. And so instead of saying, all right, so what happened to the state of the system at the previous time, and then an event happens, and how does the state changes? In a spreadsheet, you don't keep track of the state of a system. You keep track of what are the relationships that there must be, like how does one customer's arrival time relate to another customer's departure time, and you program those relationships in. So it's a very different way of programming, but by doing that, by programming relationships like these, where the arrival time of one customer is the previous arrival time plus the inter-arrival time, that relationship always holds. And if you implement that in a spreadsheet and fill down, then suddenly and almost magically, it does the simulation for you, as if you had gone through and kept track of the state at every step of the simulation. But the weird thing in here is there are no steps anymore. There's just customers. I can look at one customer and I have multiple times. So I can look and jump down to another customer and have multiple times. So this is very different than in the hand simulation, where you could focus on one time, what was going on at one time, what's going on at the next time. Now you can't really say what's going on at any one time. You just collect data across customers. So it's a very different way to simulate these things. And this isn't the way that we are primarily going to simulate with Arena, but because we are all more familiar with spreadsheets at this point in the course, then it's just showing that in principle, you can use a spreadsheet to simulate these complex discrete event system simulations. And so, and again, I walked through a lot of the formulas here, and I just skipped over a bunch of slides in this lecture because I'm just rehashing what we talked about in the previous lecture. But basically, for each column here, you can represent these relationships. And as more columns get populated and you fill these things down, then you ending up with what ends up being the whole discrete event system simulation. And it looks very different than a hand simulation, but all of the same data are in there. And so if we're to compare your hand simulation, which would be like the thing up top, and the spreadsheet, which is down at the bottom here, then we can ask questions like, what time did customer 3 leave? Well, in the hand simulation, I would need to walk through every time step until I finally saw, oh, here's an event where customer 3 is going to depart the system. Well, it looks like we've got them scheduled to depart at time 13. So from the hand simulation, I have to wait for that event to be generated. And once the event is generated, I can say with confidence, customer 3 will leave the system at time 13. But if I look down at the spreadsheet, I don't have events being generated. They're just not there. But magically, through these relationships and the way things kind of shook out behind the scenes and how the spreadsheet was run, I can look through customer 3 and I can go through and I can see, oh, customer 3 does depart at time 13. And so we see that customer 3's data is the same regardless of if I manually go through every time step or if I just put all these relationships in and shake up the spreadsheet and see what kind of comes out the sieve on the other side. And then likewise, if I wanted to ask other sorts of questions, like how much time did customer 3 spend in the system? Well, the spreadsheet says that they spent 7 minutes in the system. Well, if I look at customer 3 here, I can see that customer 3 departed at time 13, and I stamped them with an arrival at time 6, which matches what I see in the spreadsheet. And so 13 minus 6 gives me that 7 minutes that they spent in there. And if I look at my cumulative statistics, when customer 3 left at time 13, this service accumulator did increase by 7. So it all matches up. So you can keep doing that all the way through here. And so it's possible for you to check all of your hand simulation by building a spreadsheet simulation like this. And so that what we're going to hopefully see, what I'm going to hopefully talk about today is kind of motivate why, even though the spreadsheet seems so elegant, why we end up not using spreadsheets to do these very complex systems. So they work for these small scale systems, but when we want to scale up to thinking about manufacturing floors and all that, then we really need a more sophisticated tool. But before we kind of move on to that, are there any questions about this kind of review of this spreadsheet stuff, or the stuff that you were asked to do in the bonus of the homework if you chose to? And does it make sense what I mean by writing these relationships between customers across time, as opposed to writing how the state is changing of the system at every time? It's a very different way of programming, but it ends up in the exact same results. Okay. All right. So, so let's just again try to motivate how powerful spreadsheets are, but also how limiting they are. Let me jump to a more sophisticated example. So in the last example, we talked about a single channel queue. And so it was this one right here. Now we could imagine a more sophisticated network. So in here, we could say, well, we're gonna have one waiting area, but we'll have 2 servers that feed from that waiting area. And so if you are waiting for a server, you can go to either one or the other based on some dispatching policy. Now we have to come up with, all right, well, if there are 2 servers available, then which server do you go to? And so we are going to say, for this system, we'll just say that you go, if both servers are available, you go to Able before you go to Baker. And so that's how we're going to schedule these. That's how we're going to dispatch from these 2 things here. So now we have that. Let's say this is in a call center. Then how do we simulate this call center? So let's say using our spreadsheet example. So in that case, we might set things up like this, where we've got callers that are coming in. So in the spreadsheet, a lot of times your entities are going to be the things that you have in every row. And that's going to relate to these Monte Carlo things that you saw in lab 3 and that we're going to talk about more today, is that we would like to take statistics over entities. And so it kind of makes sense in a spreadsheet that each row of the spreadsheet is going to be an entity, because then that allows us to easily take statistics across entities. If we know how long one entity stayed in the system, if we average across all the rows of the spreadsheet, then we now have an average of how long each entity stayed in the system, each caller stayed in the system. So it makes sense that we're going to set up this spreadsheet for this discrete event system simulation so that our callers are on the rows. And so then on the columns, then we have to kind of define everything that we possibly would want to know about that caller that is necessary for simulating everything, as well as for gathering those statistics that we want to then analyze afterwards. And so we set up these columns here. We say, well, we know ahead of time for each caller, the inputs to the system are going to be inter-arrival time and service time, or I could say inter-arrival duration and service duration. So how long does each customer require to stay in service? Those are all the things I know ahead of time, and that's why I can populate them ahead of time. The other things I know ahead of time are the initial conditions. So there's been a question of what exactly are initial conditions in these discrete event system simulations. And in that case, they are these three numbers here. I know that the initial arrival time is 0. It's kind of like the initial clock state variable. And I know initially both servers are idle. So I am representing their idleness in this programming formulation as saying that both servers are available immediately. They are available at time 0. So that's how we write that there. So now we have all of our kind of initial information. We have our input data, so all of the inter-arrival durations and service durations. We have defined the spreadsheet in terms of our entities, which are the things we'll end up taking statistics over afterwards. And we have our initial conditions. And so now we just need to put the logic in for this two-channel or two-server queue. So the first easy thing we can do is they're going to be the same as in our single server queue. We just need to populate all of the arrival times. And we know that the relationship is every arrival time is just the previous arrival time plus the inter-arrival time. So if you were writing a spreadsheet formula for this, you might say the inter-arrival time here is going to be equal to the cell over here, which is this arrival time. You could say equals and then whatever this cell is, C3 or something like that, plus the inter-arrival time over here that's associated with this particular customer that I'm editing right now. And then I would fill all of those things down here, and then that would allow me to give all these inter-arrival times. I don't worry about it for the first one because I assume that the first caller doesn't, that would give me all my arrival times. And I don't worry about the arrival time of the first caller because I just take it equal to 0. And that's also why the inter-arrival time is blank. So that filled down here for the arrival times, and that gives me all of my arrival times. And they really are just the cumulative value of the inter-arrival times. They're just like summed up. So then I now need to do something a little more sophisticated because I want the spreadsheet to keep track of who is available when. And so I have to think of, can I come up with a relationship that I could write in every cell and just fill down? And that relationship is going to somehow represent who is going to be available for that particular customer. And if I try to come up with a general relationship, this is one of the options I could come up with. Is I could say, well, who's available right now? Well, Able is going to be available for any customer. So the customer or the caller or whatever here. For any caller, Able will be available if the time that Able is, so the when server available column here. If I just assume that I have populated these things, that these clock times are all filled in, and I know the next time that Able and Baker are available. I don't at this instant, but when I finish the spreadsheet, I will. So in the world where I finish the spreadsheet, I assume that these columns are available to me, and they tell me the times when Able or Baker are going to be available. And in those times, if I need to say for this particular caller, who is going to get that caller, then I just need to compare the availability times. And I know that Able will be assigned to that caller if Able's current next available time is less than Baker's current next available time. And then vice versa, Baker will get that caller if Abel's next available time is greater than Baker's next available time. So, and this will make more sense maybe as we populate this column out here, which we will be able to do, we just can't do yet. But we need to sort of know how things will be dispatched. And so this is something that if we had these times and say customer 3 was showing up here, if it said Abel was available at time 4, and Baker was available at time 5, and customer 3 arrived at time 3, then I know that if Abel's available at time 4, then Abel is going to get customer 3, because it would make no sense, because Abel's going to be available before Baker, so why would Baker get assigned to this customer? So that's how this column will end up being filled down. So now that I have a formula for that, which I can write in, so all of these things you can come up with, you can just use simple spreadsheet formulas for what cell represents this, what cell represents that. And so the next step here is then say, okay, well now, my next step is, now that I know who was assigned to who, then I need to come up with a when the service time began for that caller. And so this is another one of those things where we bundle a lot of logic into these max and min formulas here. And so for a particular caller, we can say, when does that caller's time begin? Well, that caller's time is either going to begin right when they arrive, which would be the case is if there's idle time, if one of the servers is idle. If that's not the case, and then in that case, the caller is going to have to wait. And so then it's going to have to wait until either Abel or Baker are available. So what we're going to ask here is we're going to say, okay, for this caller, who is available first? And so that's what this min thing does here. So we know that Abel for this caller is going to be available at this time, and Baker is going to be available this time. We want to take the one who's available first, and that goes into here. And then we say, okay, let's compare that to when the caller arrives. If the caller arrives before Abel or Baker are available, then the caller is going to have to wait for Abel and Baker to be available. And so when we take the max, then we will end up taking the availability time. But if the caller arrives after Abel and Baker are available, then in that case that we have to take the arrival time, because Abel and Baker became available and then had to wait on the caller. So this max kind of allows for the servers to be idle. So it provides for that kind of waiting time. And so that formula there, time service begin, is going to end up sort of synchronizing things. So, the arrival times and the service ending times. And once we know the service begin times, then we can calculate completion times. Because if we know when the activities begin, if we just then add to the service times for that particular caller, we can figure out when that activity ends. And that's, for Abel, that's a simple formula. So if we're currently in an Abel row, then we can say that for this caller, if Abel was the one that was chosen, it's whatever time the service began for that caller plus the current service time, which is going to be Abel's service time. Otherwise, if Baker was chosen, then we're not going to worry about Abel's completion time right now, because we're only focused on Abel at the moment, the server Abel. So in that case, we're just going to carry on down whatever the previous one was. And so that's why you see all these duplicates here, 4, 4, because Abel is only picked here. The next Abel is picked here, so we just need to carry that down. So this is a common approach when we do discrete event system simulation, where we try to capture in a spreadsheet, because we only have access to the previous row of the spreadsheet. And so if something hasn't changed, we need to copy that so that the next row of the spreadsheet also reflects that it hasn't changed. So when we move on, the previous row of the spreadsheet, which is our current row, still looks like the even more previous row. So that's why we have to do it this way. And then we can do the same thing for Baker. So we only calculate Baker's completion times if we're in a caller where Baker was chosen for that caller. And all this can be implemented using if then commands inside Excel. If open parentheses, condition, comma, true, comma, false. All that can be built into that inside Excel or Google Sheets. Now that we know when the server is complete, then we know when the servers are going to be available. Because when Able completes service, then Able will become available for the next service. So finally, now that we've figured out the completion times, we can go back and fill in the availability times. And so that's all what we do here, is that Able becomes available at the previous time Able completed a task. So that's all so you can see that this 4477, it's just shifted down 4477, and that's all that's sort of in here. And so we're almost done then. So now we know when customers arrived, we know when they got processed, we know when the processing ended. So now we can do the kind of statistics of things, and we can say, well, then how long did that customer spend in a delay? Well, we know when the caller's service began, and we know when their arrival time was. That is how long they waited for service. That is the delay. So the service is the activity, and the waiting for service is the delay. And so that's all that we calculate here. And for most of these callers, they receive 0, which means they went straight into the server. And then if we do want to know then the sum of those two, then when it's basically service time plus their delay, but another way we can calculate that is just their completion time minus their arrival time. And so this is another formula we can do for calculating that customer's total time in the system. And so that is how we would simulate a 2-server queue for a single channel of customers coming in. It's a little more complicated because there's a lot more if-then logic, and you have to keep track of which server you're focusing in on at a time. But in principle, it's doable. And it's a lot nicer, I think, than doing a hand simulation. Imagine if you were doing a hand simulation of this. You would have to generate events in that future event list every time there's going to be a departure from either server. So you'd always have to have an arrival in the future event list and 2 departures in the future event list, or at most 2 departures in the future event list. And so there's a lot more that you have to keep track of, a lot more events to process. It's just a lot more bookkeeping. So in principle, if you can do this, it's actually pretty nice to then have it all done for you. And if you want to do some additional customers, you just add additional arrival time or inter-arrival times and services. There's no more hand simulation to do. But it can get tedious for even more complicated systems. So moving forward to think about those kind of more complicated systems, are there any questions? That's the last kind of like hand simulation of a spreadsheet that we're going to, of a discrete event system simulation. This is like, that's our last spreadsheet alternative to a hand simulation. I might ask you basic questions about that in assessments moving forward, but most of the class is going to be kind of hand simulation focused, but I want to at least show you how to do that in a spreadsheet. So are there questions about where those formulas came from, or if or just in general, anything else about the spreadsheet approach to implementing discrete event system simulation? Okay. All right, so let's do an attendance question. So I'll put the URL in the chat. And so just a question to see if people are woken up. In the previous example of the call center in the spreadsheet, who were Able and Baker? So if you could just fill in one word. So the question is, in the previous example, who were Able and Baker? Or I could say, what type of simulation or you'd say, what simulation term would you associate with them? Okay. And you can either go to the URL, scan the QR code, don't hit submit, just fill that in for the, I think, first question of the attendance assignment. All right. All right, so those are some pretty simple queuing examples, but you know, we like to think about other things that would be interesting to simulate. And we, back in lab 2, were first introduced to effectively an inventory management problem. And so inventory management problems are ones where events in a discrete event system simulation usually occur at non-random intervals. And so whereas in the queuing case that I just gave you, customers arrive randomly. So we don't know when they're going to arrive. We need to know their inter-arrival durations. Usually in inventory management problems, we don't have a time component to when events happen, but there is some other random component which is often related to the quantity of things that happen at regular intervals. And so in the muffin baking simulation, we knew that muffin orders were going to arrive, whatever the time unit was, every day, every minute, whatever it was. But we didn't know how many muffins would be ordered. And so that is an inventory management problem. And so we know that we're going to open shop every day, but we don't know how many things we have to stock. We don't know how big our muffin oven needs to be. We don't know how fast we need to process these orders because we don't know how many orders are coming in. We do know that orders will come in. We just don't know how many. That's kind of the question here. So so it's a different type of simulation, but it still has a stochastic component and it still can be simulated in a discrete event system simulation model. So in our muffin case, one way we model it as an inventory management problem is by thinking about the muffin space as an inventory and the arriving muffins or arriving muffin orders as a demand. So we have a random demand, but then we have this inventory and we have to manage the inventory based on that demand. Another example of that is the kind of classic, and this is a thought model. So, you know, for some reason, you know, muffins don't sound exciting enough to go into the operations research textbooks, but newspapers do. And so if you go into an OR textbook on inventory management, you find that they often refer to the newsvendor problem. And this is also talked about more generally as the so-called single period or perishable inventory model problem. And so for this inventory management problem, we say, well, what if we have fixed prices, we have an uncertain demand, and we have a perishable product? And so in this case, in the case of newspapers, so that's the mental model you're supposed to have here, but you're supposed to be able to think of other things, but newspapers are the kind of the motivating example here. The newspapers have a constant price. We know we can sell them for whatever, you know, 25 cents a newspaper. We have no idea how many people will buy newspapers a day. And we know that if we have unsold newspapers at the end of the day, they're perishable because nobody wants to know the news of yesterday today. And so you can imagine the idea is by the news vendor, this is somebody like in the old days standing on the corner of the street saying, extra, extra, read all about it, asking people to buy the newspapers. And the question is, how many newspapers do you put into the satchel on the back of that person's back? So if you want to maximize their revenue, given that you have no idea how many people will buy a newspaper that day, but you might be able to model that, then you can say, what is the best approach for me to pack those newspapers in that person's satchel? And so the way we might approach this from a 470 approach, if you take IE 470, then you might say, well, let's maximize the expected profit. And so the expected profit, the mean profit, the average profit, is going to be the expected sale price, or so the sale price is constant, but the expected, and then into this product here, the sale price times the minimum of the inventory or the demand for each day. So each day, you're either going to run out of inventory or you're going to run out of demand. And so that is how many newspapers you can you'll sell that day. Either you'll sell all your inventory or you'll have inventory left over because you'll sell up to the demand. And you multiply that by sale price. And so the thing in the minimum here is a random variable. That's why we have an expectation here. And so that's how much money you make. But then whatever inventory is left over, you need to subtract the purchase price. So if you imagine you're a news vendor, you have to buy the newspapers and then resell them. And so the sale price is how much you're reselling them for, and the purchase price is how much you bought them for. And so this is the kind of perishable problem here. So so we model that in the kind of 470 approach. And then what we hope is that if we look at this demand distribution, if it's convenient, like let's say it's a normal distribution, if it's a convenient distribution, then we use a couple of little math tricks and we can actually calculate the expectation over that distribution. And so we can do this with some pen and paper, and we can actually solve for the average gross gains, and then we subtract off this kind of deterministic point here. So we can actually solve for this thing. And by solving for this thing, then we will then be able to optimize, because once we have a solution for that, it will have an inventory parameter. I paused the screen share by accident. It will have an, resume share. All right, it's not resuming, so let me reshare. So the idea here is that that in principle, we can actually mathematically derive the optimal inventory, because if inventory is a free parameter in this mathematical expression, we use a little calculus and we say, all right, what is, take the derivative of the expectation with respect to inventory, set that thing equal to 0, solve for inventory, and voila, that is the way you maximize your expected profit. And so that is the standard way that you might solve this inventory problem, the textbook way to do that. But then you start asking, is average profit really the thing that I'm most interested in? Maybe I'm really interested in the minimum profit I could get over any day. Or maybe I want to consider something more interesting, where my newspapers actually can be resold for some other purpose. So if it's not a newspaper, but it's kind of like a newspaper, then maybe it's not totally perishable. Maybe at the end of the day, the unsold demand or the unsold inventory can be resold at a lower price to a different market. So, so that's something that is not currently captured in this simple mathematical model. So it's those types of complications that make us think that maybe we can simulate these days. And so basically we're going to build a news vendor inside a computer, and we're going to simulate that news vendor's progress over 30 days. And then we'll say for that simulated news vendor, how well did you do? And then we can do different inventory process for different numbers for those 30 days. So we can say, well, if we would have dispatched you with this inventory policy, here's how well you would have done. If we would have dispatched you with this inventory, here's how well you would have done, and so on and so forth. And by taking these simulations and then looking at the distribution of results out of the simulations, we can get a richer understanding of all of the possible ways in which our inventory choices will affect different aspects of things that people might think are important about our returns at the end of the month. So as an example here of things that we can simulate, so we're going to simulate, well, what if there is a fixed quantity of newspapers purchased for resale each day? That's our parameter we are trying to optimize. We want to say, how many do you buy, news vendor, each day that you are going to purchase and then resell? And then we're going to then simulate that the demand, the number of newspapers purchased per day, is going to vary. And so if on a particular day, the demand is greater than the quantity you bought, then that means you bought too few, missed opportunity. Or if the demand is less than the amount you bought for that particular day, then that means that you bought too many and it's wasted production. And so we then ask the question, how does the quantity we buy, Q, affect our aggregated profit over 20 days? This is similar to asking about the muffin baking simulation, where we can say, how does the threshold for when we put muffins in the oven affect how long the muffins wait? So the simulation is going to give us a distribution of the profits we get and not just an average value. And so we can see how this Q is going to affect that distribution. So after running our simulation, we might get a histogram that looks like this. And so that's why occurrence is on the vertical axis. And this thing that says bin down here, this is our profit. And so we're saying over 20 days, we just summarized and I clicked on this and it opened up the newsvendor model. So I forgot that when I built this slide deck, I actually linked a couple of helpful sort of side things. So if you're viewing the slide deck yourself, if you click, I think, on this slide deck somewhere, or maybe it's on the previous slide, it'll actually take you to the Wikipedia page for the famous newsvendor model. You can read more about that if you're interested. But so for this histogram here, we can see that over the 20 days, then we got this distribution. Some days, so 10 of, so basically what we did here, notice that there's 10, 78, 145, 129. The way we interpret this is we ran the newsvendor for 20 days, and then we ran that 20-day period for, and I forget whatever number this adds up to. So let's say, off the top of my head, we'll say 300 times. And so you imagine 300 universes where in every universe you've got a news vendor who is looking at their profits across 20 days. And that's what the histogram that we're looking at here. And we can see that in 4 of those universes, they made a lot of money. In 10 of those universes, they did not make that much money. But in most of the universes, they made around the average amount here. And so we can see that the average value is around, I don't know, $150 or something like that. But if we really needed to know that, like, in order for us to survive to the next day, like you might say that this poor news vendor, in order for them to be able to buy newspapers the next day, they need to make a certain amount the day before. And if that certain amount is $100, then that's going to show us that actually there are a set of universes where the news vendor did not make that $100, and as a consequence may not have been able to survive to purchase papers the next day. So that's how this distribution can be much more informative to us than just the average. So that's the first kind of major inventory management problem you should be familiar with. So that's the first kind of class of inventory management problems, is the news vendor type problems, or the single period perishable problems. So if you go into operations research, you'll see that term again, the news vendor problem. The other big inventory problem that we see, and you'll do some more, you'll actually do simulations in Arena of this one later on in one of the later labs, is the so-called order up to inventory management problem. Before I get to that, are there any questions on anything, things that I meant here about the news vendor problem? About what this, or the basic idea that we're not actually focused on newspaper sales, but we're using newspaper sales as a model for whenever you need to stock up an inventory of perishable goods. You know that those goods might perish before demand is available to purchase them. And so there's a risk in buying too many. And that's what the news vendor problem is trying to capture. And you can either solve it in a static way, like in this kind of expected value way that you do in 470, or you can think of it in a more dynamic way, where you kind of end up capturing all of the possible things that could happen, not just the average thing that happens. So questions? Okay. News vendor model. Remember that. All right, the other big inventory management problem that we see in this class a lot is the order up to problem. So in this case, the question is, how often do you go to your warehouse to check the inventory, and what should your target inventory level be? I'm sure a bunch of you have had this experience where you go to a store and you're frustrated in seeing, or even worse, let's say this happens to me all the time. Let's say I use my phone to order coffee and a pastry or something like that ahead of time, and because I'm using the phone's app, in theory, I can see their inventory on the app. And so I go and I say, all right, it's pumpkin spice season, so I'm going to order a pumpkin cream cheese muffin. And it says on the phone that this store has the pumpkin cream cheese muffin. Now, I don't leave the house that much, but I make this and say, okay, but I'm going to go out, I'm going to run down to the local Starbucks or whatever the coffee place is, and I will then get my pumpkin cream cheese muffin from Starbucks because they said it was available and now they're reserving it for me. And then I get there, and then of course they say, oh, I'm sorry, the app inventory wasn't up to date. Turns out we don't have the muffin available to you. Is there something else? And then so I might say there's nothing else, and the sale that they thought they had, they now lose because I asked to be refunded. And maybe the other thing that I ordered, a coffee, I say, you know what, since I'm going to end up making a different lunch choice anyway, and then I end up not taking the coffee as well. So this can be a major problem, is your inventories not having up-to-date inventories. But then the question is, how often do you have people going and looking and double checking what your inventories are? And so that's really what the order up to problem is all about, is how often do you see that you've got the pumpkin cream cheese muffins available, and how many pumpkin cream cheese muffins do you order to make sure that they will be available when you see that you're low on these muffins. So that's getting a little complicated because now I've almost merged the two because the pumpkin cream cheese muffins are perishable. So you can imagine making this even more complex. But for now, I'm not focused on the perishable side. It's just the order up to. So the idea here is I've got this, this graph here where over time, we've got our amount in inventory. That's the solid line, this kind of sawtooth line here. And what we see here is that naturally over time, there's going to be ordering events. And so we see that over this N here, then I say, well, these are the number of days or whatever I wait until I replenish that inventory. And so during that time, as people are buying from the inventory gets depleted. And then I order some quantity Q1. And then that replenishes the inventory, and the inventory goes low again. It might even go negative. So we have to go in back order, and then I order up again as well. And so the question is, how many of these, how Q1, how many do I order, and how often do I check? And a lot of times this is often complicated by the fact that when you order them, they don't show up immediately. You might say, we need more muffins. And then Starbucks Central says, okay, they'll be there in 2 days. So then you have to deal with the fact that you've noticed you're low on inventory and it's going to take you 2 days to get that inventory repleted. So you're probably going to have to go a day without muffins. All right, so that's the problem that we would like to solve. So in the book, they focus on refrigerator sales. And so each N days, you order enough refrigerators to bring the inventory back up to M units. And orders take several days to arrive, that's so-called lead time. And so that lead time is something that we're going to randomize. So we know on average it takes a certain number of days, but sometimes they come quicker and sometimes they go faster. And each day, customers demand a random quantity of the refrigerators. So that's the other random thing that we're going to put in here in the stochastic model. So lack of inventory leads to back orders or lost sales, and we can penalize those as performance metrics. And having too much inventory can be costly too. So we can actually penalize inventory that is standing. So we can say that we have to pay rent on the amount of space that we have available. And so if inventory is just taking up that, then we're still gonna have to pay rent on that space. So we better be making money off that space by selling inventory out of it. So if we have unused inventory, then maybe we have to pay actually kind of a price or at least some penalty on that. And we can put that into that performance metric. And so the causal question here that we address as operations researchers, remember, research always follows from a question. That's why I'm defining these causal questions. So the operations research causal question is, how does the policy, the MN ordering policy, so M is what we're ordering up to and N is how often we're ordering, affect the frequency of back orders? So we're focusing on the frequency of back orders, which are which could also be viewed as lost sales. And so this is something that we also then can run a simulation to simulate. And I'm not going to show you results from that simulation because we actually do this simulation in Arena a little later in the semester. But I just want to motivate it for you so you've got it in mind. So are there questions about this order up to problem? Does this make sense where the portions of randomness are and why we might want to use simulation to better understand how to solve this problem? All right, so why I wait for questions here, let's do another attendance question. So again, I put the URL in the chat. It's also available here on the screen or via that QR code. And so in this question, what I'm asking here is what does the variable, or what does the parameter M, as in Mary, represent in the order up to inventory problem? And so this is the problem we just described. Said that the parameter M is one of your decision variables, and then there was another parameter N, as in Nancy. So what does the parameter M represent in that problem as presented by the book for the refrigerator sales? All right, so while we sit there for a second, any questions? In the back half here of the lecture today. And I just want to introduce Monte Carlo sims next, which is what you've seen in Lab 3. All right. All right, so very lecture-y today. Just rolling on through here. So the next thing that I want to introduce you to as a target for simulation, and the reason I'm bringing these all up together is that they're in a chapter of the book where they demonstrate that all of these can be solved with relatively simple spreadsheet examples. And so that inventory problem, we're going to further embellish when we do it in Arena to make it even more complex. But at least here, we can actually do all of these inside a spreadsheet. So you are introduced to Monte Carlo simulations in Lab 3, which was yesterday, and those Monte Carlo simulations you executed. I mean, people who've turned them in already have already executed them on a spreadsheet. And so these are just some examples of things that in principle you could do in a spreadsheet that are not necessarily discrete event system simulations, but I still would fall under kind of would be related to stochastic simulation. And so Monte Carlo simulations are kind of the classic example of this. These are static, so again, they're not discrete event system simulations, they're not dynamic, but instead you can view them as you run a lot of different outcomes and you look at the distribution of outcomes, and that's what tells you something interesting about the problem. So each Monte Carlo run is like a game of chance. And that's where the term Monte Carlo came from, is that, as I kind of explained in the lab video, is that back when they were developing the atomic bomb, they needed stochastic simulation methods for the computational work that they were doing. They hadn't been developed yet. And so they then said, well, you know, we can make use of randomness in this novel way to speed up our computational methods. But in order to have a code word for them to talk about this, they then labeled this as the Monte Carlo method. And Monte Carlo is a reference to a famous casino where you have lots of games of chance. So that was meant to be a code word for that, and it's just stuck ever since then. So now when people talk about Monte Carlo simulations, they're basically talking about simulations where your simulation acts like a game of chance. It somehow sometimes comes up one way or comes up the other way, and if you play enough of them, then you end up getting a picture of the system. If you play enough games of chance, then maybe you might end up winning, but you rarely win at a single game of chance. It's useless to run a single Monte Carlo run. You have to run 1,000 Monte Carlo runs to make sense of it all. It's bad to run a single, pool at a slot machine. Or to make any money at a slot machine, you have to sit there for a long time in order to get any win. And you still might not win, but you'll at least get the full distribution of winnings if you sit there for a long time. So the example that is in the book is a reliability problem. And so the reliability problem here is you've got a milling machine and it's got 3 ball bearings. Each one of those ball bearings can fail. There's a failure time distribution. So each one will fail after a particular amount of time. So those of you who've taken courses in quality or in reliability should be familiar with this idea that things fail at different times and we can model their failure time distribution. And so we are then interested in, when do we replace the ball bearings? Do we wait for the failures? If we get a failure, do we replace them all at once? Do we replace them ahead of time, assuming that there might be failures in the future? And how we make up our minds is going to depend on how much the ball bearings cost. They're going to depend on how quickly we can replace the ball bearings and how expensive the labor is going to be. So how does the replacement schedule affect our total operational costs? So we know how much the costs of a single replacement are. How much does it affect our operation as a whole? That's something that we might want to model in a spreadsheet or in a simulation. And so the Monte Carlo experiment that we're going to run is we're going to calculate the cost of 45 ball bearing replacements. And so what we've done is we've simulated the lifetime of each simulated ball bearing by drawing it randomly. So we have a distribution of lifetimes. And so for every ball bearing, we draw from that distribution. And we repeat this process for 45 ball bearing replacements. And so, and then we have 3 different schedules that we want to compare. So we can say, let's wait for every ball bearing to fail and replace it. So even if we replace one and the others are right there, we're going to leave them in there and wait for them to fail. Or we can replace all 3 of them. If we're in there replacing one, we might as well replace all 3. Or instead of that, we're not going to wait for failures. We're just going to replace them on a regular schedule. Of course, if they do fail, we'll replace them when they fail. But otherwise, we're going to try to catch them ahead of time. So we preemptively replace. And so we might test a hypothesis, and that hypothesis might be that accumulated downtime and labor costs are greater than the gains from operating the ball bearings for their full lifetimes. And so if we have a hypothesis, that's a predicted answer to our question. So our question, how does the schedule affect this? Then we can make a prediction in accordance to that hypothesis. If that hypothesis is true, then if all bearings are replaced at the same time, then the total accumulated cost will be less than if ball bearings are replaced as it fails. That's our prediction. And we run the simulation to evaluate whether that prediction held up. And if it doesn't, then we can reject the hypothesis. And so in our spreadsheet, what we do is we create a row where each row is 3 failure times. The 3 failure times of the 3 ball bearings. Just like we had an Able Baker, those 2 servers, and they had like 2 times that they'd be available. You can think of that as we got 3 ball bearings in the row, and these are the times that each ball bearing is going to fail. So each Monte Carlo sample is the lifetime and delay accumulated from 15 of those rows. So 15 times 3, that gives us our 45. And so one of the questions we need to then ask is, how many chunks of 15 rows do we need in order to make a good inference? And that is a statistical question that we will address after the midterm, but it basically has to do with how variable this result is going to be. If we see that across chunks of 15 of these 15 rows. So you run 15 rows, you see what the outputs are. You run another 15 rows, you see what the outputs are. If the outputs vary tremendously as you go from one set, which we view as a simulation, to another set, then you're going to have to run a lot of sets. You're going to have to run a lot of Monte Carlo runs. And that's just because in order to deal with more variation, you need more samples. But instead, if we notice that over a small set of runs, that every Monte Carlo simulation gives us roughly the same number, then we don't have to run that many Monte Carlo samples. I'm hoping that you saw this, like say when you were calculating pi in the first problem of the lab. Or for those who haven't done it yet, I hope you will see it. I asked you, I forget how many runs, if I had to do 1,000 rows or 10,000 rows, And you can think of each row as an outcome of an experiment where you're estimating pi. And so the variability there from row to row to row is that, some of are going to be way off from pi in one direction, the other is going to be way off from pi in the other direction, and that's why you need to run so many rows. If instead we were calculating something which every row was already pretty close to the actual value, then we only need to run a few to hone in on that value. So the variance in our simulation will determine how many simulation runs we need to run. So when you come to me after you're about your final project and you say, how many simulation runs do I need to run? I'm going to ask you, how variable are the outputs you're measuring? And we will do something called power analysis to help us get a more quantitative prediction of how many runs we need. So that's all coming up. All right, so the other example that they had in the book for Monte Carlo runs were these bombing examples. And I think I'm going to skip over this example because you can read about it in the book, but I've put some of these here, but just to prevent this from getting a little too old, a little too quickly, we're just going to skip over this example. And but the basic gist of this example is given that you have a particular area and you're dropping bombs with a particular distribution, you want to calculate how likely is it that your bombs will fall in that area. And you can do that in a spreadsheet as well. And the last one example that I do want to go over, at least briefly, because it is the Lab 3 activity, the part 2 of the Lab 3, is these activity networks. And so hopefully these were well enough described in the Lab 3 video, but the basic idea here is you frequently in manufacturing are going to have parallel activities that come together at the end and they wait on each other in order to finish the process. So if you're making breakfast, you often might say you can make eggs and you can make toast and you can make bacon. If these are things you eat for breakfast, you can do all those things in parallel. They have different steps. So maybe making eggs takes 3 steps, making toast takes 2 steps, and bacon is only 1 step. But you can't serve all of them until they're all done. And so then the question then is how long does it take for you to make breakfast, given that breakfast has 3 components that run in parallel? And so what you end up modeling in Lab 3 is a distribution for each one of the small steps of the activities. And then you join those all together to see how long the breakfast takes. And so we can see that there's a uniform distribution between 2 and 4 minutes for the first step of the eggs, for the second step, and for the third step. So altogether, the average time of the eggs is 9 minutes. But you've got variability in each of the 3 steps. Likewise, for the 2 steps, we have a different distribution between 3 and 6 minutes for the first step and between 3 and 6 minutes for the last step. So again, 9 minutes on average, but broken up in 2 steps instead of 3. And then finally, for the last one, it's between 6 and 12 minutes. Again, an average of 9 minutes, but it's 1 big step. Now you look at all of that and your intuition might be that the average activity is going to take 9 minutes. But what you'll actually find is that the average activity will take longer than 9 minutes, and that's not a numerical mistake. When you combine things this way, and we'll talk about this more later, when you combine things in parallel, then you tend to wait on things more often, and that additional weighting is going to end up increasing your times. And so and this is actually going to relate then to like how do we understand the distributions of times that come out of each one of these paths. And so the lower path we know is a uniform distribution between 6 and 12 minutes. But what you would find if you took a histogram of the upper path is that the histogram of the upper path looks more like a bell curve. And that bell curve, both of these paths have an average of 9 minutes. But the fact that the lower path has a lot of mass out here above 9 minutes is going to be one of the reasons why your average time for all paths together are going to end up being longer than 9 minutes, even though the average for each individual path is 9 minutes. So what I'm hoping that you'll see with this as you do that lab is that there's magic that happens in summation. And so when you sum things that start off in square distributions, then they end up looking more and more bell-shaped over time. And that's why the total distribution across the top path ends up looking like a bell curve, even though across the bottom path it's a square. So the top path has got a square, and a square. You add those distributions together and you get a bell curve. Now, does anyone remember from, say, 380 or 385, some interesting statistical something that has to do with adding up random variables? Like, how do we describe what is a mathematical result that, I see some results coming in, so keep them into the chat. So what is a mathematical result that has to do with adding up random variables? Independent random variables. Can you either remember what happens when you add up a lot of them together, or what that general result is called? And I can wait, because I want all of you to have this in the back of your mind as you complete this assignment, complete this lab. Anybody, give me one more answer from somebody. Somebody else. All right, yes, so I'm looking for central limit theorem. I'm looking for they all become more bell-shaped, more normally shaped. And so just keep that in mind, is that when you're simulating this activity network, what you're implicitly doing is you're simulating the summation of 3 independent random variables. You're an independent uniform and plus an independent uniform plus another independent uniform. And this histogram is the histogram of activity times from that summation across the top. And already by adding 3 of them together, their original square shape gets distorted and gets turned into a bell shape. And hopefully this simulation helps give you some more intuition as to why that's happening. But then there's this outcome of that when you then combine them in parallel with things that aren't being summed, then you end up having this interesting effect where the top path will end up being completed more often before the bottom path, even though they both have the same mean. So I just want you to focus on that as you do that activity. And this is just one of the other examples of what you can do in a spreadsheet. You can do simulations of these activity networks. And the way you're going to do that in the lab is in every row, you're going to store a draw of basically all 3 times for the upper activity, the 2 times for the middle activity, and the 1 time for the last activity. And so there'll be 6 of those random draws. And then you'll be able to add those together. So you'll be able to say, okay, for this top activity, it took this long. For this middle activity, it took this long. And for the bottom activity, well, I know how long, it's just the random variable. And so once you've got those 3 durations of those 3 activities that happen in parallel, then you can say which activity took the longest. And that sets the total duration for the breakfast as a whole. And that's what you'll end up doing in the rest of this. And again, there's an interesting question on how many Monte Carlo runs are enough, and that depends on how variable your results are per run. If they're not very variable, you don't have to run that many runs. If they are variable, you have to run a lot of runs. In this one, I tell you how many runs to run, but in real life, you're going to have to do a pilot study of the variability of your outputs and then use that variability to help you predict how many more runs you need to run. And that's something that we'll talk about how to do that after the midterm. So that's part of the kind of more statistically focused part of the course. All right. So before we go to the last couple slides here, which are moving forward, are there any questions about any of the spreadsheet stuff or about the difference between Monte Carlo simulations and discrete event system simulations or anything? Okay. I can tell you the lab 3 result is one of my favorite results. So if we have time after the lab is turned in, then I've got a post-lab lecture where we'll talk about that. And it's one of my favorite results because I remember when I was in your shoes, when I was forced to do an assignment, which made me do something that where the central limit theorem was, I suddenly saw it in simulation. It suddenly made it make a lot more sense to me. And it opened up my eyes to how crazy things can happen when you think about distributions that you don't see when you just think about means. So I can tell you that lab 3, it may seem kind of dull, but at least for me, this is one of my kind of favorite assignments or labs, because I feel like it's so simple and yet it has the potential to be so illustrative. So any other questions? Okay, so last couple minutes here. All I really want to say here is I just spent the rest of the time talking about all the cool things you can do in spreadsheets. So why the heck do we get rid of spreadsheets? Do we stop using spreadsheets in the rest of the class? And basically in the short, long and the short of it is, well, that the systems we work with are going to be so complex that it is going to be difficult for us to come up with simple spreadsheets and then make quick modifications to them. If you think even about a fast food lane you can order in sequence or you can order in parallel. You might design a simulation in sequence and then someone asks you, well, what would happen if instead we built our fast food lanes so that we ordered them in parallel? And then you'd have to do that analysis. After that, then they come to you and you're consulting for them and they say, okay, now we want to order ahead. Now we want to install an app and have orders taken from there. Well, how do you deal with that? If you had to keep, modifying these spreadsheets, then they're really inflexible. They're easy to build the first time, but then you almost have to build a totally different spreadsheet when you need to make a simple modification. Look at the changes when we went from a single server to 2 servers in the examples where I started in this lecture. It's like a totally different spreadsheet. So whereas in Arena, if we go from 1 server to 2 servers, it's easy. So we're looking for more sophisticated tools that allow us to handle the complexities of life and allow us to very quickly modify them without having to do a lot of extra work. So that's kind of where we're going. And so these packages, basically, if I jump to the end here, they automate a lot of the repetitive tasks that we would do in spreadsheets. They include high-level components where all the work has already been done for us, and they usually have attractive graphical options that go beyond just a table of numerical results that maybe you might graph. And we already saw how you can do 3D visualizations in one of the first couple of lectures. Now, you'll still use spreadsheets to analyze the data coming out of these things, because it turns out that although Arena has some statistical tools built into it to allow you to kind of do a quick t-test or a quick ANOVA, they're not great. And so you still need to use R and SPSS and SAS and Excel to do the statistical analysis. That's really where it's strongest. And so when you're going to generate results for me in this class, I encourage you to actually do that, to find ways to download data out of Arena and analyze them in a separate tool rather than just using the Arena tools, because the Arena tools are very, very limited when it comes to stats, but they're great when it comes to programming. So really these things are kind of complementary. All right, next we're going to talk about agent-based modeling, and then that'll allow us to then finally gracefully slide into discrete event system simulation. So look out for that coming up next. But that's all I've got for you today. So I'm happy to take a couple of questions, but let me give you the last attendance exercise for today. And so again, I'll put the link in the chat, and that attendance exercise is explain to me where does the term Monte Carlo come from? So the question is, where does the term Monte Carlo, when applied to simulation, come from? So why Monte Carlo? Why didn't they just call it random sampling or something like that? What was the reason for the use of Monte Carlo? And with that, if anyone does have questions, I'm happy to take them. Otherwise, that's all I have for you today. And so you can feel free to pop off the chat, and I'll see you next time. And have a good weekend. All right, any other questions?
Just a quick one.
Yep.
Should we expect that we can't backtrack in the exam?
In the exam, I haven't written the exam, and I don't think I've written an online exam for this one, but for the exam, it is unlikely that you wouldn't be able to backtrack. In the exam, I'll probably just give you a giant dump of questions and you'll be able to scroll through, because that's kind of the experience you would have in class. And so for the exam, that for the Canvas activities, their purpose is different, and they're meant to kind of guide you forward and those sorts of things. But for the exam, I would think it'd be highly unlikely that I wouldn't allow you to backtrack. And for the exam, I'm just going to dump all the questions at you, and then you'll be able to move through, but you'll have a fixed time to get them done. And in not all the Canvas activities will there be a restriction on backtracking. And on many of them, then you'll just get all the questions. There was a question in the chat about, can I repeat the second attendance question? And I would have to look back to make sure of which one was the second, but I think the second one, and if it was that I asked what parameter does M represent in the order up to inventory model. But in general, if you miss an attendance question, kind of the idea is you can always go back and look at the recorded videos, because you've got 24 hours to submit these things after I post the recorded video. The recorded video doesn't get that processing until later in the night. I usually process them pretty late, and then you got 24 hours after I post them to then go back, and you can rewatch and find that spot and then submit the attendance question. Okay. All right, looks like that's about it. So I guess I will end the meeting now.